Hello, Mrs. Hahn. This is our energy project. This is Spencer Smith, Noah Nagum. We are Group 6. So our objective for this lab was to design a 3D ramp that was at least 15 centimeters tall and had the least amount of friction with the most energy efficiency.
Our setup, so we did a 3D printed model which was 17.5 centimeters tall with a rubber ball of a diameter at 2.5 centimeters, which was placed at the top of the ramp with a railing that was going down the sides of the ramp to keep the ball in a straight path. And that path was 20.8 centimeters long that it traveled down and 11.24 centimeters in length. And the photo gate was at the bottom with the laser touching the exact bottom, leading to LabQuest, which went to the iMac with Logger Pro.
So what we had to do with the photo gate to get the most accurate reading was place it perfectly perpendicular to the bottom edge of the ramp, raised up to the center of the ball where the diameter was truly 2.5 centimeters. And that is how we would get our most accurate calculation for kinetic energy, comparing that to our potential energy of the ball being at 17.5 meters high.
So the equipment, obviously we use the 3D printed ramp with the photo gate and the Logger Pro software. We also used a metric ruler to measure out the diameter of the ball. We used a scale to measure the weight of the ball and a calculator to do all the calculations, other than the velocity, which the LabQuest did for us.
So our procedure, we kind of already explained. We positioned the laser at the bottom of the ramp, perpendicular to the edge, raised up to the center of the ball as it passed through. We set up Logger Pro with the photo gate in timing mode to get the velocity. And we just put the ball at the top of the ramp, let it roll down. We repeated that last step a couple times to compare our data and get the most accurate reading. But then we just use simple mathematics to calculate the kinetic and percent error of our trials.
We took the initial potential energy at the top of the ramp, which was using the equation mass times gravity times height, and then we compared that to the final kinetic energy, which is 1/2 mass times velocity squared at the bottom, to see the amount of energy that was conserved from the top versus the bottom.
So after running it a couple times, our best data came out to 1.891 meters per second. That was the velocity of that trial. And our velocities were a little bit all over the place just due to human error, releasing the ball. It probably would have been a better option to use the metal ball because the rubber one was kind of bouncy and just not as uniform. But anyway, we did end up with a velocity of 1.891 meters per second, and that gave us a very good efficiency.
So the data obtained, the velocity of 1.891 meters per second, and the potential energy that we found at the top of the ramp was 0.01715 joules. And then we found the kinetic energy at the bottom to be 0.01740978 joules. The initial position being 17.5 centimeters high. We found the energy efficiency of the ramp to be 98.5% when we compared the two potential energies and final energies, and then the total percent error of the experiment was 1.515%.
And I mean, we may have been able to get a slimmer percent error, but it was more about our setup of the experiment, making sure we didn't have any outliers and making sure that we minimized the human error as much as possible, which really came down to the positioning of the laser. I mean, if we had the laser a little bit too high or a little bit too low, we would have gotten a different velocity, and in some cases that could have given us a better percent error or a better efficiency, but then it wouldn't be accurate. So we went for the most accurate, true data we could get by, placing everything to the best of our ability in the exact position it needed to be to give us the most true reading. So that is how we got our percent error.
And then the analysis, as we said before, shows an energy efficiency of 98.5%, which shows the system is very close to the ideal ramp of 100% efficiency. It is very close to outputting the same amount of energy that it initially started with. The energy conservation shows that in an enclosed system, the energy will not be added or lost. It will be equal to the initial, and it was very close to the initial.
So it was very close. I mean, this was in theory an enclosed system, and the whole objective was to design a ramp with the least amount of friction and highest energy efficiency. But the truth is, there obviously is friction. It's impossible to make it completely frictionless on a 3D printer. So the minimal amount of friction that it did have definitely factored into our percent error. And that was a result of coming out of a 3D printer and being a rubber ball. Like I said, we probably would have had better results with a metal one.
And then continuing the analysis, the difference between the initial and final energies, we found them to be 0.0002957 joules, which shows that the initial energy is very close to being the same as the final energy. So this shows that the energy is very close to being conserved and that it is indeed a enclosed system.
So yeah, our results show that without a doubt, energy is definitely conserved when you have a 100% enclosed system. So our sources of error, like I said, were the rubber ball being one. It had a seam around the ball, which probably threw off it rolling down the ramp and maybe added a little bit more friction. It also had a dimple in it, which affected how it rolled down the ramp. And like I said, the 3D printer can only print so finely, so the ramp was a bit coarse, which affected how the ball rolled down the ramp. And our means of measurement were not 100% precise because all we had was a metric ruler, which only gives you tenths of a centimeter, and our eyeballs. So you can only do so much with that.
It could have been a lot more accurate if we would have used a vernier caliper, because that would have gave to 100th of a centimeter, which would have led to more accurate results.
100%. And then we did our best to position the laser in the proper position, but I believe we used a protractor to place it perpendicular to the bottom edge of the ramp and measured to the center of the ball properly. It would have helped us out a little bit more. But anyway, that is how we did this experiment. If we did it again, those are probably some of the things we would change.
Thank you, Mrs. Hahn.
See you tomorrow.